Good afternoon, good day, everyone, wherever you are. I hope you're enjoying a nice afternoon. So I think many of you has, looked after Code for Earth over the last couple of months, and we are very happy and very proud to present today in our midterm webinar some first results. And I'm here with my colleague Esperanza. Esperanza and I, we are coordinating Code for Earth. And for those who are new to Code for Earth, just a very, very quick background information. Code for Earth is a key innovation action run by the ECMWF, the European Center for Medium Range Weather Forecast, and is also supported by Copernicus and Destination Earth, two programs of the European Union. So each summer, we welcome individuals and developer teams from different backgrounds in earth science, computer science, and software development. They work on some challenges identified by mentors and colleagues of ours. So it's all about collaboration, innovation, and open source development. And then if the teams have successfully completed the projects, they can receive, or they will receive, a 5,000 euro stipend. This is in very short what it is about. And here, roughly the timeline. So we start the entire program with a call for participation, usually in March. And that goes for about 6 weeks, where people, can ask questions and then hopefully submit a proposal, which then will be evaluated by us and the mentors. So the second step is that in April, late April, we usually announce the selected proposals, and then starting in May for 4 months, we have the coding phase, which we are actually in right now. And then we have a final day event in September. As mentioned, we are in the coding phase, and we are more or less in the middle of the coding phase. And thus we are having the midterm webinars. Before we go into the, into the projects, I would do a big shout out and thank you for all our mentors this year. We have colleagues from ECMWF, but also from outside. And without their expertise and their time and their excellent collaboration also with the teams, Code for Earth would not be as successful and could not happen. So big thank you to all our mentors. I would like to hand now over to Esperanza.
Yes. Hi, everyone. We are very pleased now to have here today 5 of the 10 selected projects in this edition 2023. So 5 projects are in the spotlight today. It is in the slide: benchmarking surface heat fluxes, diffusion models on weather bench. TropiDash is a project towards a comprehensive tropical cyclone hazard dashboard. The 4th project here today is the compression of your spatial data with varying information density. And the last one is atmospheric composition dataset explorer. But there will be another webinar next Wednesday, 12th of July, when we can have the rest of the teams, the 5 teams, and we will introduce a description of the projects, their ongoing projects and their progress, the first outcomes. These 5 projects, stay tuned, is for the next webinar, will be the projects Fire Forecasting, Deep R, Deep Reanalysis, Sketchbook Earth, Illustrated Climate Chronicles, Chat ECMWF, and TESE-RAC. So we are looking forward to the second webinar. And now, the coding phase started in May and finished at the end of August. But this is not but there's another fourth step in the Code for Ed program. It will be the final Code for Ed day. It is planned to be the 20th of September. It's a celebratory completion of the program. And stay tuned. All the details will become in the website, because this event, the 10 projects, will showcase, release their very well shaped and innovative development. So we are very looking forward to the 20th of September, when all these projects will present their outcomes.
Yeah, and it will be online
Yes.
accessible as well.
Exactly.
So,
it's a streaming event, so all of you are invited to join us. Yes. So remember, to know everything about Code for Ed, you can visit. All information is on our website, but also you can check our social media, Twitter. I think you can see the account on the chat, or LinkedIn, and also GitHub. All the projects are on GitHub, and you can follow the resources there, the code. Very well. So this is about us.
yes.
So I'm very pleased to present the first project of today.
Nice.
Is benchmarking surface heat fluxes. Yes, the developer is Laura Mack. So Laura, the floor is yours. I hand over to you. Please describe your progress and what have you found. So.
Hi, Laura, just 1 second. Just to everyone, all the attendees, while Laura is presenting, as well as the other speakers later, you have a Q&A dedicated chat. So if you have any questions, please just write them. And, at the end of each session, we will just read the questions and the speakers can then reply to you. Thank you very much. Thank you, Laura. The floor is yours.
Okay, yeah, thanks for the introduction. Okay, yeah, as already mentioned, my topic is benchmarking surface heat fluxes, and I work with Jasper, David, and Christoph on this project. And I will start with a general background. So our general aim is to develop a framework for benchmarking land surface components of weather or climate models, with special focus on ECMWF models. And there is already a Python package called Landwehr for this, which allows for the validation of soil temperature and soil moisture. And what we want to do is to extend this package for surface heat fluxes. And there are 2 types of surface heat fluxes, as visualized in the graphic. So sensible heat flux and latent heat flux, and they are driven by temperature or moisture gradients between atmosphere and surface. And they are influenced by, for example, climate and weather conditions, and especially also by the surface properties. So, for example, orography, and very important is vegetation and the moisture availability. Yeah, and these fluxes can be modeled. So with land surface components of a weather or climate model. And for this, we use here ERA5 LAN, which is run online, fully coupled with data assimilation. So, but the fluxes are not assimilated here, so it's still somehow independent. And it has a spatial resolution of 31 kilometers and the temporal resolution of 1 hour. And additionally, we use another model, short HYFS, or hydrological forecasting system, which is run offline and driven by ERA5 and contains the updated vegetation scheme. And it has the same spatial resolution, but the lower temporal resolution, just 6 hours. And these surface heat fluxes can also be measured. So that's a bit more complicated than normal meteorological stations. So for this, we use eddy covariance measurements. This means that you have such a sonic anemometer with a really high sampling frequency combined with temperature and water vapor measurements. And a portal which provides such measurements is ICOS, the Integrated Carbon Observing System. And they have like all the flux towers in Europe. And these are really point measurements. And they have, in the end, the temporal resolution of 30 minutes. Yeah, and here you can see in the left plot the location of these stations in Europe. So they cover a nice north-south range. And on the right plot, you can see that when the network started in 1996, there were just 5 stations. But in 2020, we had now 67 stations. So, and we will use 2020. Okay, and yeah, as an introduction, an example for a general seasonal or also quite similar diurnal cycle for sensible and latent heat flux. So here you can see on the x-axis the month and on the y-axis the flux in watt per square meter. And you can see that on first order, this follows solar radiation. And the positive sensible heat flux means that we have unstable stratification. And the positive latent heat flux means that we have evaporation or transpiration from plants. And this is the usual case in summer and during day. And you see in winter or also during night conditions, like we have slightly negative fluxes or close to zero fluxes. And this means in terms of sensible heat flux that we have stable stratification, or in terms of latent heat flux that there's condensation or deposition. Okay, yeah, then let's start to look at some results. So here we look at 0 and 12 UTC values. They should like be an example for showcasing the diurnal cycle. And we look at like a station and then the nearest grid point in the model. And on the left side, you can see the linear correlation on the y-axis. And on the x-axis, the stations sorted by their latitude. So from the southernmost to the northernmost station. And you can see in the different dot types, like you can see the 12 UTC and 0 UTC values. And you see for 12 UTC, both sensible and latent heat flux have really high correlation of more than 0.6. But for the 0 UTC values, the correlation is on average quite low, just below 0.3. And if we look now at the mean deviation, then it's the other way around. We have a low mean deviation for the 0 UTC values, which is due to that the fluxes are quite low in general. But because they are so low and close to 0, it's quite difficult to get a high linear correlation. But for the 12 UTC values, we have a high mean deviation. So up to like minus 130 for sensible heat flux. But because they are high and positive, we still have a good correlation. And yeah, so these differences in 0 UTC and 12 UTC measurements motivate to look at the daily average values. So this is now the same plot type, but the daily average over all these like 4 measurements like 0, 6, 12, and 18 UTC. And again, on the left side, the linear correlation versus the location of the station. And now you can see that on daily average, the correlation is more than 0.7 for both fluxes, and just a few Mediterranean stations have a really low correlation. And if we look at the mean deviation, we see that this is slightly positive for latent heat flux, which means that the model slightly overestimates on average the latent heat flux, and it's slightly negative for sensible heat flux, which means the underestimation. Yeah, and if we now combine seasonal and diurnal cycle, here's an example for one selected station in Finland. And on the left plot, you can see the measured sensible heat flux. So the month on the x-axis and the hour on the y-axis. It's interpolated, but just in principle, these 4 values we always consider. And you can see this clear maximum during summer for the 12 UTC measurements, and negative values during night or also during winter. And if we look at the mean deviation of the model from these measurements, we see again that during day conditions, we have this negative mean deviation, which means an underestimation. And during night, we have positive mean deviation, which means a slight overestimation. So in general, the diurnal cycle is not as strongly pronounced as in the measurements. But what we also see is that these absolute values are much higher in summer than in winter. And yeah, now this was all on this hydrological model. So if we combine this or compare this to ERA 5, that's a big table, but maybe if we look first at the last row, for example, this is again the daily average values, then you can see that for ERA 5 land, for sensible heat flux, we have a slightly higher linear correlation, but also slightly, in absolute value, slightly higher mean deviation. And for the latent heat flux, the values are quite similar. But the biggest difference is that if we look at, for example, 12 UTC, then the linear correlation for ERA5 is much lower than in the other model, which is probably related to that this is really an hourly resolution. So it's much more difficult to reach this high correlation on an hourly basis than on a 6-hourly basis. And so here would be interesting then in the next step to adapt the resolutions of both models. Okay, to sum this up, so what we did so far is we did the post-processing of the model and the observational data and the data exploration. And as showcased here a bit, we did the evaluation of some standard metrics for daily average values and the diurnal cycle. And currently that's in the framework of some Jupyter notebooks. And what we plan to do is to put this now in this actual landware package and add in this landware package also the diurnal cycle and probably some slicing per vegetation type. And scientifically, it's interesting to compare the results and to the study here of Kral 2011, where they did a similar thing for ERA interim. And there it would be interesting to see how or if the models improve to this slightly older model. Yeah, so that's all. Thanks.
Thank you. Thank you very much, Laura. I think you are progressing so much. We are quite impressed about your first results. And if everyone has a question about the project benchmarking, please, you can add your question in the Q&A chat. And
yes, hi, Speranzatina. There's already a question in the Q&A. Can you see it?
Well, it's just a correction.
Yes, it was one of the mentors, David. Yes.
Okay, yeah, sorry.
Yes, David commented that you're comparing aerophyte, not aerophyte land.
Yeah.
Offline.
Yeah, thanks for the notice. Yeah.
Yeah, and how is your experience with your coding experience with your mentor? Is the mentor Laura? Can you share a little bit about it?
Yeah, it's definitely really good. So I really like that we meet regularly and discuss the progress. And also it's nice to like that the data is already provided and that you can directly start with the programming and I don't have to do too much data work. So that's really nice. Yeah.
Okay, fantastic. Okay. We are looking forward to the end when the coding phase finishes and you can share with all of us your well-safe progress, the project. Thank you.
Yeah, if there aren't any questions right now for Laura, you still can, I guess towards the end of the session, we might still have additional time. So if you want to, if you have more questions or you come up with a question on benchmarking surface heat fluxes, you can still type your questions for Laura into the Q&A window and we'll take it from there, or Laura can answer that online. Yeah, you can.
Okay, now it's time for the second project. It's diffusion models on weather bench. Jonathan is with us. The floor is yours. Please describe your project, how the first outcome you can share with us. The floor is yours.
Yeah, thanks for the introduction. I hope you can see my screen now.
Yes.
Perfect. I will go to presentation mode and then let's start. So if I can already say I forgot our mentors on here, and I want to thank Jesper Dram, Gloria Pino, and Matt Chantry, who are really a great help. And let's jump right in. So I think probably all of you have played with one of these online AI image generators. They all kind of work in the same way. You put in some kind of conditioning information, which usually is a text description, might also be an image. This gets then fed into a machine learning model, a special kind of machine learning model called a diffusion model, and this then produces various images. For example, you could ask for an image to illustrate a presentation, and then you get some more nice results. And what we want to do is basically apply this kind of methodology to predict the weather. In our case, of course, the conditioning information would not be a text, it would be a weather state. Then we feed this into the diffusion model, and we want to get out multiple weather forecasts. Okay, before I describe in more detail how we do this, I think it's worth to spend some time at least on how diffusion models work. So if we have an image in our training set, what we do then is usually we add various or increasing amounts of Gaussian random noise. And because this addition of the Gaussian random noise is somewhat similar to diffusion, this whole class of machine learning models is called diffusion models. And what we are interested in the end is, of course, not to go from a cute looking cat to random noise, but we want to go from the random noise and step by step build up some good looking image. So the question is like, how do we reverse this? How do we go from noise back to the image? And this works as follows. For each of the images in the training set, we just first choose randomly one of these noisy versions of the image. And we then give our neural network the information that gives it some conditioning information. In this case, we would tell it, for example, the original image that we put in was a cat. And then we ask the neural network, just given this noisy image and the class label, to split up the noisy image into a part that the network thinks is the true image and into pure noise. And then, of course, we can compare the network prediction with the true image and compute a loss function and adapt our neural network parameters to make the predictions better. And of course, we don't only want to do this for a single image, we want to do it for every single image in the training set that we have. For example, we might have another image of a cat, choose a different noisy version here. We might also have other classes, for example, an elephant or a dog. And after the training is finished, we can then use the neural network that we've trained to build up the entire images. So what we then feed in would be like a randomly generated noise vector, and we would put in like the kind of class that we want to have in the end. For example, we could say we have a class, and then step by step, our neural network would make the noise less noisy and more cat-like. Now the thing is, I think most people at Code4F are not primarily interested in images of cats, but in weather. So the question is, how do we adapt this to weather now? The first thing that we change is that we use different conditioning information. So instead of providing a class label, what we provide is something that actually helps us make weather predictions. And this is, of course, how the weather is like at the moment. So we feed in the current weather, and we feed in maybe also what the weather was like a short time ago. And then we sample a random noise vector. And then hopefully, if our training works well, we can use this and predict a future forecast. Okay, so what's the data that we train this on? It's called the WeatherBench dataset, and it was created as a benchmark challenge to benchmark different kinds of machine learning models for weather forecasting. And the task is basically to predict whether 3 days or 5 days ahead. WeatherBench is just a subsampled version of ERA 5, subsampled, I mean downscaled, no, not downscaled, interpolated causal resolution. And the resolution, the closest resolution in the dataset is available is 5.6 degrees, which then corresponds to 64 pixels in the longitudes and 32 in the latitudes. And we have a time step for every hour. And the temporal extent is as follows. We use the years 1979 to 2015 to train our method. We validate our method in the data from 2016, and we test on 2017 and 2018 data. And there are a lot of different variables available, including, for example, geopotential height, temperature, relative humidity, and all different kinds of wind speeds. And most of these fields are even 3D, meaning that we have multiple pressure levels or multiple heights, kind of. And of course, we cannot use all of this data because it's just huge. Therefore, we need to select a subset. And in all of the results that I will show later, we only use geopotential height, and we use a sub-selection of the pressure levels that are available. Yeah, and as I already said, due to the large size, we also had some problems in the beginning, but we think mostly solved this right now. Okay, so I think I still owe you to tell you what actually is compared on WeatherBench in the WeatherBench data set. So the metrics that are computed there is mainly the root mean squared error. There's more, but let's focus on the root mean squared error, and it's evaluated for 2 variables, which is the geopotential height at 500 hectopascal and the temperature at 850 hectopascal. Okay, so how do our results look like? Before we see how our results look like, let's first have a look like what a true result would look like. So this is what we are aiming for, just a random selected time step of the geopotential height at 500 hectopascal. And our prediction looks like this in this case. So we can see the overall shape of the diffusion model that the diffusion model produces is very good. So I think if we don't have any labels here, we couldn't really tell them apart, but we can see some differences. For example, in the Southern Pacific here, we can see that the structure is not exactly identical. And we can see this difference also if we subtract the two from each other. So we can see here that the difference is lowest in the tropics and the differences increase if we go to higher latitudes. And just to show you that I didn't just cheat by picking one good time step, we have a second time step here. And we can see that, first of all, the patterns are different. So the network doesn't predict the same thing for every time step, which is already a good thing. And then we can see that, again, we sort of match the structure of the target well, but there are, again, some differences, and we see similar patterns in the differences. Okay, one nice thing about diffusion models is that we can produce ensembles. So in the example that I used to illustrate the approach, I put in one sentence and I got back 4 images. Right now we can do the same thing. We can put in one weather state and we can get out a whole bunch of ensemble members. And then ideally we can do some analysis on this. We haven't really done this in detail. Just for illustration purposes, I just show like the standard deviation of the ensemble here. So we can see that the standard deviation is highest in the regions where also the network is not really sure what the deviations between the predictions and the ground truth are largest. As WeatherBench is a benchmark data set, there are luckily also already a few methods that we can compare to. And this is what I will want to show in this plot. So what this plot here is the performance as a function of the lead time, and the lead time is also the amount of time we want to predict into the future is given here in times of days. And what we plot on the y-axis is the root mean squared error of the geopotential height at 500 hectopascal. And yeah, just to say smaller is better in this case. And the first thing I want to show in this plot is the operational ECMWF model, which is of course the thing that everybody tries to beat with these numerical weather, deep learning weather prediction models. And so the top model that has an entry in the WeatherBench data set is the following. It's by Russ Venturi. And also, I want to give one more model. This was the paper that introduced the WeatherBench data set, had also some methods inside of it, and this was the best performing method, was this cross and this cross. And now the question is, where are we on this curve? And we are here. So that means that our performance is still worse than, quite a margin worse than the best model on WeatherBench, but we already match the best version that was introduced with the original paper. And we can all, of course, see that the farther we predict in the future, the harder the task gets. So there's still quite some room for improvements. Okay, then let me finish by telling you what next steps we are planning to do. Of course, if we try to beat a benchmark challenge, we want to get better results. And a bunch of papers, for example, GraphCast, ForecastNet, and Pango Weather have found that if you go to even higher resolutions and throw a lot of computational effort at the problem, you tend to get better results. So what we want to go is to like finer resolutions for the first step, which is of course memory demanding and which might make us use latent diffusion, which is like a special kind of a diffusion model that was very successful. Also, many of these online image generators are based on latent diffusion. We might look into different models we can use as a backbone for diffusion models, and we can, right now we have a very small subset of input variables, and we would like to expand this at some point in the future. The second thing we want to look into is how we evaluate the model. And because we have this nice ensemble prediction aspect, I think one thing that's definitely worth looking into is how to evaluate these ensembles nicely and also maybe focus on large impacts and extreme events. And the third and last point is that we want to go from predicting single time steps to predicting trajectories. So the way we do it now is we train a single model to go from the initial time step like 3 days ahead, for example. And ideally, we would want like one continuous trajectory of the weather, like for 1, 2, 3, 4, and so on hours. And there are basically 2 approaches we have in mind for this. There are special diffusion models that can be used for predicting videos. And the other thing one could do is train a model and then apply it iteratively. So feeding its output back into its input. Yeah, this was everything for me. If you have questions, I hope you have questions, and then I would be happy to answer them.
Yeah, thank you, Jonathan. Nice presentation. And indeed, we have questions. So we have 2 questions, and I would go immediately to the questions. So Filippo Dainelli is asking how you decided the training and validation test set division.
Yeah, so we did this to be compatible with already existing approaches. So we just copied the methodology of somebody else. There's reasons why you would want to split it this way. For example, it makes sense to keep continuous splits in time, so that you don't shuffle it. Let me open it. So you don't want to shuffle the time test split and validation set, because otherwise the neural network could use information from the training set to infer on the test set. Yeah, I think this is the main point. And the second question, I think, is about the number of diffusion steps. And this is in fact a hyperparameter, and yeah, we keep it fixed to 1000 at the moment, which is, I think, a standard choice.
And then Nicolas Masterantonas has also a question. Very interesting, Jonathan. Thanks. It seems that the model has challenges in the mid-latitude. Would it make sense if you train regional models with finer resolution for those regions rather than for the whole globe, and somehow combine the results? Somehow?
Yeah, it's also something that I thought about. I think in the end, it's probably easier to do it globally, because if you do it regionally, you need some way to combine the information from like adjacent patches. So for example, if there's like a storm system coming into your regional model, you need to somehow give this information to the regional model. And yeah, so this is, you don't have this problem in a global model. And right now we're not really limited by the memory. Once we reach the point, we might also go there. There are some papers that use vision transformers that actually split up the images in different patches. So yeah, there are some people who explored this already a bit.
Okay, good. Thanks a lot, Jonathan. There are right now no more questions, so I would, round of applause. Then I would like to introduce our next speaker. That's Paolo Colombo, and he works together with Filippo Dainelli and Laura Paredes Fortuny on the project on TropiDash towards a comprehensive tropical cyclone hazard dashboard. Paolo, the floor is yours.
Hi, sorry, and we also receive a comment from Felipe Cabello. Amazing work. Would love to see the performance related to anomalies. Just let you know.
Okay, that's a recommendation for Jonathan. Maybe you can take this into consideration and report on that on the last day, on the final day event. Good. Paolo.
Okay. Hi everyone, my name is Paolo Colombo and I'm present you TropiDash, a comprehensive tropical cyclone dashboard for tropical cyclone. Our team is composed by myself, Filippo Dainelli, and Laura Paredes Fortuny. I and Filippo come from the same university in Italy, while Laura is from Spain. And the project purpose arises from some concerns considering the current availability of tropical cyclones risk, outward information, summarized in single location and dashboards. More in particular, current dashboards lack featuring multiple products coming from multiple sources. The charts represented usually lack interactivity, reducing user experience and exploration of the data displayed. Current dashboards are very specialized, excluding less experienced users from effectively interact with these tools, and expanding the possible data to be visualized and creating different level of complexity in the chart can increase the accessibility of the dashboard to a broader audience. So following these 3 main limitations, we present the project purpose, which is to build a Jupyter Notebook dashboard to help in preparedness and resilience against tropical cyclones events. Let's start with some introductory information regarding the events at the center of our project. So tropical cyclones. Tropical cyclones are intense circular storms that originates over warm tropical oceans. They are characterized by low atmospheric pressure, high winds, and heavy rain. You can see at top an image of a satellite picture of Cyclone Freddy, which occurred in the southern Indian Ocean last February. On average, about 85 tropical storms occur along the year across the globe. The map in the bottom displays the region of formation and the red general tracks of the storms, which have different names depending on where they occur. Tropical cyclones are much relevant for civil protection because they are big threats to life and property, even in the formative stage of their development. They include a number of different natural hazards that can individually cause significant impacts, like high seas, extreme winds, storm surges, heavy rainfall, tornadoes, and floods. To give you an idea about the impacts, according to the World Meteorological Organization, over the past 50 years, 1,942 natural disasters have been attributed to tropical cyclones, which caused more than 700,000 deaths and 1,400 billion in economic losses. So our project wants to build a dashboard, and the project structure is developed through 3 milestones. The first milestone covers the gathering of all background information needed for the development of the project itself. And this means having a clear idea of which are the hazards related to tropical cyclone events, which are the relevant indicator of and meteorological parameters for the description, what are the current tools available, and visualizing tropical cyclone hazards and what are the strengths and weaknesses of these tools. So the second milestone ensures a clear design of the platform that we want to develop, listing all the components and how they interact with each other. The topic addressed are how the data sources are assessed, which is the structure of data visualization, and which Jupyter plugins to use. The third milestone in the developed structure platform online with appropriate documentation. This will be the more operational phase where we will implement the design decided by reaching the second milestone updates on the platform. So in the first, which we concluded last month, consisted in the recognition and analysis of existing dashboard showing tropical cyclones data. What we have retrieved from this phase is that having too many variables make it harder to understand the dashboard and most important information we can provide. Lightness and speed of the dashboard in providing maps and coverage is important, but maybe the dashboard could be divided into different basins of interest. Summary characteristic for each cyclone position helps in better understanding the data. Impact layers are necessary. Colors are helpful for visualization of intensity categories, and it is overall important to dedicate different plots and charts to variables that cannot be visualized as overlaid to a map. And at last, it can be important to increase complexity of the chart while you scroll through the dashboard, so that experienced user can go to the end of the dashboard, while a non-experienced user can just remain on the tools that they actually can understand. So from the existing context recognition, we also identified a list of variables and indicators we believe would be important to include in order to have a comprehensive and complete ensemble of information on tropical cyclone hazards visualization. In this slide, we report a few of them. To give an example, we decided to group them in 3 macro areas: cyclone properties, meteorological and ocean variables, and impact variables. So then these variables can be mapped and indicated to assess the possible risks connected to tropical cyclone. To design the platform, we followed these steps. We are now finishing the platform design phase, and at first we understood and decided how the platform will access data. We'll gather ECMWF data through an API. Then we decided on the data visualization structure, deciding the graphs to show. The variables listed before will be plotted in maps and bar plots, depending on the variables, and leaving to the user the possibility to interact with maps and graphs. After exploring possible plugins, we decided to use Voila to deploy the dashboard, as it enables the possibility to be launched by terminal and permits an overall flexible framework to build the final dashboard structure. Then we define the dashboard structure and use a user interface by defining how maps and graphs will be shown and accessed by the user. Here we can see a first visual draft on what we expect to obtain as a Jupyter Notebook dashboard, together with the key features we want to have. We'll produce a more precise draft to be included in our second deliverable, but now I'm going to deepen some key features. We want the dashboard to have 5 sections, 3 of them with plots and maps of the different variables categories following the previously cited division, so cyclone properties, atmospheric ocean variables, and impacts. The first as a global section, where the user is able to overlay all the variables present in the dataset, and the fifth one as a map, where the user can choose a location to plot the temporal evolution of some variables. We want to build an interactive widget for the map selection, where the user can choose the latitude and longitude boundaries of the map and automatically visualize a crop of the global map. And we want the dashboard to have different information buttons referring to information menus, a general one and specific one for each section, to improve user experience and understand how to use the dashboard. We want to have a panel reporting all the summary cyclone characteristics as the user selects the event to visualize. For example, most intense category reached, minimum sustained wind speed, maximum sustained wind speed, minimum value of low pressure, and so on. So this is the overall idea of our design. We will, as I said, we will develop more and put it in our second deliverable. But now on the next phase, so the platform design will be finished next Monday on the 10th of July. Then we have scheduled our last milestone to be completed on the 31st of August, actually developing the dashboard, like coding the Jupyter Notebook dashboard and ensuring the maintenance through documentation. Then on the 10th, on the 20th of September, we will have the presentation, the final presentation in Bologna. And now on, if you have questions, I'm here. Thank you so much for your attention.
Thank you, Paolo. Great presentation, and I think a lot of interesting topics to consider to bring into the dashboard. There's a question on the general chat. So Garima is asking if you have noticed any effects of the cyclone on the emission of sea salt aerosols. Not sure if you can answer that question.
I actually cannot answer this question, but maybe my colleagues can, because I don't actually work on cyclones, but maybe if you leave us an email, we can write you. Because right now I have no idea how to answer this question. But
yeah. So so far, what was the biggest challenge for you, Filippo and Laura? You would say, okay, this you know, what's the biggest obstacle and we came it, or you know, is there something you can say about that, or everything smooth?
It was everything was actually smooth, but the most difficult thing for me was like to condense all. Because there are a lot of tools already available, which were the good things about these tools, which were the bad. So to condense all of them and to find out, okay, we want to take the good and leave out the bads. was not that easy, but we managed to do that, and so now we are keen, and we have a good idea on what we want to do, and we are starting now the coding phase, and we have energy, and we will we'll achieve it.
Great, thanks a lot, Paolo and your team. And I would like to go to the next presentation. So Ayub Fatih, he will present on the compression of geospatial data with varying information density. And, you know, having personally a background in, I'm a geographer, so yeah, I'm interesting to see how far you have reached in that. So Ayub, the floor is yours.
Thank you for the welcome. Thank you for everybody for joining today. I am Ayub. I have recently graduated with a degree in geomatics and surveying engineering. In this year, Code of Earth edition, I am working on compression of geospatial data with varying information density. I am very fortunate to have the guidance and supervision of Hauke, Milan, Juanjo, and Miha to wrote this project. So for my presentation, we will begin by introducing compression, why we need it, and what is it exactly. Then we will delve into the bitwise real information content-based compression, which promises exciting possibilities, followed by a presentation of the challenge I have been working for 2 months now. And lastly, I will conclude by sharing some preliminary results. So the exponential growth of data across multiple fields has created a demand for efficient data management. And according to the ECMWF website, an astonishing 200 terabytes of atmospheric data are being added daily to the archive. To address this challenge, compression, also known as source coding or bitrate reduction, plays a crucial role. It involves code information using fewer bits than the original representation. And by compressing data, we can achieve several benefits, such as saving disk space, reducing the bandwidth usage, and improving overall system performance. And the compression involves a trade-off between the precision, that is the information content, the size, usually the disk space, and the compression speed. The goal is to achieve optimal results in all aspects. However, in practice, the aim is to strike a balance that suits the requirements of the application and the available resources. So before getting further, I want to remind you of how floating numbers are stored in memory. It is actually similar to scientific notation, but is in base 2 with the small catch in the exponent. So the first bit is reserved for the sign. If it's a 0, the number is the positive. If it's none, as in this example, the number is negative. The next set of bits represent the biased exponent. It controls how far and in which direction to move the decimal point in the fraction. And the exponent is represented in a biased form to allow for positive and negative exponents. The bias is a function of number of bits reserved for the exponent. And the biased exponent is then used to calculate the actual exponent's value, 2 to the power 4 in this case. The remaining bits represent the mantissa, also known as the significand or fraction. And these bits represent the fractional portion of the number in binary form. So for the bitwise real information content-based compression, it is done as follows. A first step is the bitwise information, that is the mutual information between the bits is calculated. So a bit position contains more real information. The stronger the statistical dependence to the adjacent bits it is. Then we keep only the bits with real information and discarding the bits with the false information. After that, we apply our lossless compression. To visualize these steps, I have taken this graphic from this paper of Clover and al. So we work with the gridded data from Cartesian, curvilinear, or unstructured grids, and we utilize the binary representation for efficient storage. So, and the second step is analyzing the mutual information of adjacent bits position, and we identify the key bits that are the significant bits that preserves most of our real information. And finally, we remove the false information bits by rounding them to 0, ensuring effective compression. Another example for clarification. So we can start with a one-dimensional bit stream of data. Using the concept of mutual information, we identify and retain only the significant bits that are in the middle in black here. And then the compression can be thought of something like this. And by applying this approach, we compress the data from 160 bits down to 60 bits. To illustrate this further, I will share an example with code. So for this, we will be using xbitinfo, which is an X-array wrapper around the bit information GL to retrieve and apply bit rounding from within Python. The package intends to present an easy pipeline to compress datasets based on the real information content. And also to note that bit information GL was developed during the summer code edition of the years 2020 and 2021. And the dataset used for this example is the 2-meter temperature in Kelvin from the ERA 5 dataset. And you can get it from the Copernicus climate data store. And the data type is float 32. So the first thing is getting the information content per bit. As we can see, the first bits contain no real information. So in the last portion of this image. And then the values start relatively high and start decreasing near the end. For the second step is we get the key bits. And the key bits, as I mentioned earlier, refers to the number of bits from the mantissa that are necessary to retain most of the real information. In this particular case, the key bits value is calculated to 8 bits. This value is then utilized to round the original data using the XR bit round. And then we can go to the compression. So the original size is stated as 64 megabytes, which can normally be compressed to approximately 34 megabytes, resulting in a compression ratio of around 2. However, when compressing the bit-rounded data, it results in a size of 4.1 megabytes, achieving a compression ratio of approximately 15. And here in this example, I am showing water vapor from the CAMS dataset, specific humidity compressed in the longitudinal dimension. And we observe a transition from preserving 100% of the information on the left to 83 on the right. The purpose of this demonstration is to showcase the impact of this method of compression. And as you can see in the right-hand side, the visual representation appear very pixelated. However, this highlights that we can easily preserve around 100% of information without sacrificing any crucial details within the dataset. The challenge I am working on is the continuity of the compression method using bitwise real information content that has been developed during last edition of 2020 and 2021 by Miel and Clover. And this year I am working on the development of an information density adapting compression by implementing compression and bit information retrieval on a chunk basis, analyzing the information density of climate variables across time and space, and studying the optimal chunk size depending on different features like hurricanes. So for my preliminary results, I will be showing in this analysis. So chunks possess key bits values that are approximately similar to the key bits value of the entire dataset, which is the expected outcome. However, we are working on developing a metric to assess whether chunking provides superior results. And in this analysis, however, as a part of our ongoing work, we are actively developing a metric to evaluate this performance. And this metric will help us assess whether chunking provides this result in terms of information retention and compression efficiency compared to analyzing the dataset as a whole. And for this surface pressure, similar observation can be made for this variable as well. And in the second, like in the third step from our goals, we have examined the impact of chunking on specific features as hurricanes. In this case of the ERA 5 data, we analyzed the hurricane. So we did not observe any significant differences in the variance of key bits values for the chunk where the hurricane occurred. However, we suspect that for higher resolution data and smaller chunks, we may observe variation in key bits value. So further investigation is required to confirm this hypothesis. And similar findings can be observed also for the mean sea level pressure variable, as mentioned in the previous slide. And for a summary, the bitwise real information content-based compression can be done by calculating the bitwise information and getting the key bits, discarding the bits without real information, and then doing the compression. And chunking can enhance this compression. And for the next step, we will explore higher resolution datasets and smaller chunks. And we will analyze the information density of climate variables and the effect of chunking, as most of the code is ready for now. And this is my last slide. I'm happy to take any question if there are any. Thank you.
Thank you. Thank you very much, Jeff, for your presentation. Very, very nice. You have a lot of results so far. So we don't know if there is any question specific
no, I
for
don't
you
see at the moment.
So what is the big challenge from this project? This is a follow-up of, this is the third year of this compression data project. What has been your big challenge? Because you are only one person as participant, as developer.
Yeah, so actually it went really smooth. So The one thing that was not very much a challenge, but just the learning curve. So at first, I didn't know much about the bitwise information compression and that. So the learning curve was a little bit steep, but yeah, it's all going smooth. And I want to thank again all the mentors that are doing tremendous work. Yeah.
Yeah, but it has been a learning experience as well so far.
Yeah.
So perfect. Thank you, Ayub.
Thank
we have with us the five projects with us today. It is Atmospheric Composition Dataset Explorer. So the developers, the coders are with us. It's Elisa Aliverti and Julia Fiantenese. So the floor is yours, and when you're ready, tell us about your project.
Thanks. So I'm sharing the screen. Should be this. Can you see it full screen? Okay. Okay. Hi. So we are Elisa, Julia, and Luigi, who is not here with us today. And yeah, our project is the Atmospheric Composition Dataset Explorer, or for short, Atmospheric Explorer. And we have a lot of mentors that we thank very much for their support. Why?
Sorry, Lisa, I
Yes.
think we are not able to see your screen. I think it's all dark. Can you please try to share it?
Oh, okay. Yes, I can try again.
Yes.
Is this fine now?
Yes.
Okay. Perfect. Thanks. And so the motivation of this project, of this challenge, which was challenge 11, is to create an application, an interactive applications for users to interact with some data sets and create atmospheric composition diagnostic plots on demand. The problem behind this, let's say, the motivation behind the challenge is that there are these huge data sets that both researchers at ECMWF and other end users would like to be able to explore and understand more better and quicker. And also to make it easier to prototype new data products and understand how this data is behaving, get insights about the data quality and so on. And also, of course, to create quickly plots also for research papers and any other users. So the goal is also to have a very flexible tool that can be used by these different end users. And flexible is also in the sense that it should be quickly adaptable to other data sets in the future to, as I said, explore new data sets and have all the same functionality also for other data sets. And the problem is that these data have a high volume and complexity. All these data sets are a bit different among them. So it's not easy to generalize these functions. So that's what we are trying to do. This project builds upon last year's Wildfire Emission Explorer, which was another challenge from, last year it was not called Code for Earth, but ECMWF. And the Wildfire Emission Explorer was working with these wildfire emission datasets. And the idea now we want to extend this idea to other datasets, and mainly these two datasets, the global greenhouse gas fluxes dataset and the atmospheric composition reanalysis. So they are different, and the data access method and the format are different. But we would like to have a final interface like there was for this Wildfire Emission Explorer, where you can select the country, the data type, the time period, and the reference period, and finally produce some plots. Yeah, and now I'm leaving the floor to Julia, that is also here, and we'll talk a bit about this, the data sets that we're using and the plots, that some plots that we have produced so far.
Yeah, thank you, Lisa. So starting from the proposal of the challenge 11, we have started with some plots proposed in the challenge itself. And among all the plots, we choose to show now 2 plots, one for each data set considered. So this one is the first plot proposed, is a time series plot, one for each countries. This comes from the inverse optimized data sets. This data set is scientific interesting because provides mainly free gases in terms of concentration, mean column, and fluxes. And in this plot, we are focusing on fluxes. So here, considering the CO2, so yes, yeah, I can move on, Elisa. Okay, thank you. Considering the CO2 fluxes from this data set, it's possible even to choose which kind of source these fluxes came from. So here we choose anthropogenic, so fossils flux, but the users can choose different kinds of flux. So for example, agricultural sources or natural sources, biological, etc. And with the blue line, we represent the air samples measurement, and with the orange one, the satellite measures. With the gross line is represented the spatial average. In this sense, for each country, there is a spatial average, and the area around the gross line represents the confidence interval equal to 95%. In this sense, it is possible to keep in account the spatial variability for each country. So this is may helpful for scientific or any kind of user to have an immediate evaluation of trends for different origins of gas fluxes, and also from different countries for different sources, and also with different kind of measurement. The other plot we've considered instead is from the other data set, that is the atmospheric composition reanalysis. We choose to present here the ozone mean column, total column, and it's quite representative and also important in terms of scientific consultation, also for mainly referring to the stratospheric ozone, so related to the variation during time after the CFC pollutants, and also referring to this particular stratospheric circulations and transport. So mainly here is reported an off-Moller plots. So for on the y-axis, we have the latitude, and on the x-axis, the time. We have chosen like time step, month, but users can choose any time of time step, so daily, weekly, monthly, or yearly. And for each time steps, there is for each latitude an average value of ozone for that latitude. So it's averaged on longitude value. So this to reach these plots that starts from the other data sets, it was necessary to make some operations on it, starting from the conversion to a more common and intelligible unit. So we convert the original dataset unit of concentrations to DU that is used for scientific use. And we also have to do some cartographic operation, like shifting the longitude that is its original expressed from 0 to 360 degree to minus 180 plus 180 degrees. And here is presented as the discretized color bar. So with the from the minimum to maximum concentrations. And all these plots are made from basic from Jupyter Notebook, and then it is improved as API. And so now Elisa can deepen these aspects.
Yes, thanks, Julia. So as Julia said, we have produced these plots with Jupyter notebooks that test the APIs, but our core goal is not to have Jupyter notebooks, but a Python library with these interfaces. And that is modular and can also be used in the future, as I said, for other data sets and other plot types, for example. So this is a very raw screenshot of the structure of our files so far. And yeah, there is also a new file. But basically, we have divided the architecture in 3 layers that follow an ETL pattern in some way. So we extract the data or download it from the datasets through CDS API. Then we transform it. And for example, what Julia said are some transformations that we need to do to the data. And then we load it into plots, for example, so because our end goal is to have plots. And we are using also some software best practicing, like trying to test as much of the code as we can with PyTest and adding documentation and block strings. And we are creating it as a Python package that can be easy to install and use it in other environments. This is the link to our repository if you want to check it out. Although I'm not sure it's public yet. I have just thought about it, but we can make it public if it's not. And finally, I also want to mention that we have thought about using EarthKit, which is a library developed by researchers at ECMWF, because some of these functions can also be, well, already exist in EarthKit. And that is one step that we have in mind. We first wanted to try it out with very raw functions, but of course, we hope to have the time to try it out, also to use it in these APIs that will make it a bit more stratified in some way. And also something else we want to improve for next steps is the caching, because right now we are downloading all the data, not every time really, but not in a very optimized way. So these are 2 points of improvement that we have in mind. We have also started creating a UI application with Streamlit, which is different from last year's Wildfire Mission Explorer that was made with Voila, but we wanted to try it out Streamlit. So now I see if the video works. I'm not making it full screen because I'm afraid of what might happen, but I hope you can see it. So this is our first draft of the application that uses the APIs, which can also be accessed with CLI and with other Python plots. But the idea is to have this very easy interactive interface from which the user can select, as I said, a country or an area, then a time period, and it takes some time, but then you can choose the plots that it creates. And yeah, let's see how long it takes. It shouldn't be long now. Yeah, and then the plots are made with Plotly, which makes them a bit more interactive. You can zoom in and see the data by hovering the mouse on it. So that's the main next step, finishing this interface. And we, okay, not again, we have finished. So thanks. And we are looking forward to any questions.
Thanks a lot, Elisa and Julia, for a very interesting presentation. And I already, the perspective you provide with the last of the video. Very good. So there's a comment from Miha. He loves the Streamlit example. Grazie. So are there any questions from the audience to Elisa or Julia? So if so, please post it in the Q&A part. Yeah, what again, you know, same question as Esperanza had for Ayu. What was your biggest challenge so far? Where you say, okay, that was something you did not expect, or something, you know, what was that? Or did everything work smoothly? That could be also the case.
No, that's never the case. Let's be honest.
That's for be honest.
I think I can answer, although if Julia wants also to add something, she's welcome. For me, one of the biggest challenges was that these data sets are so different one from the other. And so generalizing them, which is the core of the challenge, is really hard. Even just understanding how to access the data exactly and to have the same APIs that apply to different data sets is surely still a work in progress. And even to think we have to make it as general as possible, even for the future, is something that's always on our mind. And yeah, it can be hard for many different data sets.
Yeah. Okay, thank you very much. And we have still one question to the previous speaker, to Ayub. There is a question, Kiko. So Ayub, I see you're typing, but maybe you can also come online again. And actually, you know, if all the speakers would like to come online, you're welcome. So Kiko writes, thanks for the slides. Would it be different to work with scalar or vector fields in terms of information compression?
Yeah, thank you, Kiko, for the question. So I think working with scalar fields and vector fields may present different challenges and consideration in terms of compression. But I'm afraid I don't have an answer for this question, as we have been working just with the graded data. Yeah, so I don't know if anyone has an answer. Please feel free to share it.
Okay. Good. Are there any other questions? So none that I can see. So I guess I'm sharing my screen right now. So then we come to the end of the first webinar, and I want to thank all our speakers, Laura Mack, Jonathan Weider, Paolo Colombo, Ayub Fatihi, Elisa Aliverti, and Julia Fiantanese, and I hope I pronounced everything correctly. It was very, very interesting and inspiring to have an insight into how far you have already come with your projects. And I really look forward for the final day event in September. But before that, so to everyone, an invitation next week, same time, same location, more or less. We would like to invite you to the second webinar, where we have presentations about the current results of the remaining 5 projects. This is fire forecasting, deep reanalysis, Sketchbook Earth, Chat, ECMWF, and Tesseract. So once again, applause to all our speakers and of course the mentors. And anything else, Esperanza?
Yeah, we hope to meet you on next Wednesday with all of us, because we are very curious
Yeah.
to see the progress of the 5 remaining projects. So well done. Yeah.
Okay.
Well done.
Thank you very much.
Thank you.
Bye bye.
Thank you. Bye bye.
Thanks. Bye.